Welcome, everybody. Thank you for joining me on another episode of Axioms on Trial. Today we'll be discussing the nature of mathematics, whether math is discovered, invented, a combination of both. I want to thank my guests for joining me today to have this conversation. Dr. James Franklin, Dr. David, and Daniel Perez. If you guys maybe provide a little bit of a background to the audience listening in so they know a little bit about you, and then we can get right into the conversation. So, David, you want to go first? I know you've been on here before.
Sure. So I'm a physicist or an astrophysicist. I study black holes.
Okay. Dr. Franklin?
I'm a retired mathematician and philosopher in Sydney, Australia. I know little physics, but I have a background in mathematics, probability, and history of ideas.
Great. And Dr. Perez?
Yes, I'm Daniela Perez, and I do astrophysics, basically black hole astrophysics and cosmology.
Awesome. Thanks again for to joining me in this conversation today. So I'm always been interested in math. My background is philosophy. I've always sort of struggled with understanding math myself, I'm using this as an opportunity to hopefully learn more about it and what it is that people believe about it. I'm interested in what your views are on what it is that we are doing when we are using math, what is a tool of math, and whether or not it is capturing something true about the external world. Are abstract objects things that exist, or is that just a confusion of language? David, maybe we can start off with you and we can go around the panel. What is your view?
Sure. So I'm obviously not a philosopher, and I don't think very deeply about these kinds of things. But often you hear people say that math is a language, and I think even physicists will say something like that. Mm-hmm. And usually I'm not that okay with that idea. And if I think about it a little bit, I realize that it bothers me because if I think about the English language and I think about playing around with words, I don't imagine myself getting at truths about the world. Whereas, and we can get into this, whereas playing around with mathematical structures that seem to apply to the physical world in one respect, then when you're playing around with those structures in a completely different domain, you discover things in the math that then seem to apply to the real world. And so you're discovering something about the real world. So the word language sort of bothers me in that sense. Also, I can easily imagine a world without the English language. Right. I was born in Italy, and my first language is Italian, and I can easily imagine never having spoken English. But surprisingly, if I try to imagine a world without math, then I struggle. What kind of a world is that? I will try to make the simplest world. I immediately imagine some kind of thing over here and some other kind of thing over there, perhaps different. But then immediately I start to see that I'm dealing with groups, and math applies to different kinds of groups with different properties. And I start to immediately imagine patterns, and math applies to patterns. So it's very difficult for me to imagine a world without math, whereas a world without the English language is completely straightforward. And so I don't like the word language. Maybe something like rules is better. I see them as being very different. Math is somehow some kind of set of rules for understanding the world, for understanding possible worlds, something like that. That's sort of a physicist perspective, and maybe you guys can put me straight.
Sure. I'll say one thing, and then I want to hear from everybody else in response to what was just said. When I think of language, it's not so much that we couldn't do without the English language or the Italian language. I think one theory of language is the idea that there is some inherent structure to all languages that all languages share. I'm not saying that I necessarily believe this. I'm probably agnostic on these matters. But it's the symbols themselves, I think, are dead. But what they're trying to express, or what the symbols are attempting to correspond to, may be something that actually exists. So while we could do away with the English language in particular, there may be something deeper that all languages share, that language as a tool may be corresponding to something that's out there.
Sure, maybe I just want to add that, but you can easily imagine a world without any language, right? In fact, our planet existed without any language for a long period of time, right?
Yeah, of course. Of course, no, I just view language as a tool to hopefully capture something about the way things potentially are. Dr. Franklin, what are your thoughts?
Yeah, I agree entirely with David that it's not a matter of mathematics is not a matter of language, but that it captures some real aspects of the real and the physical world and any other world there may be. So that's a good thought experiment to go back before there was language. Let's think about the world of the dinosaurs, where there was no humans and no language to think about it. So are there mathematical properties in that world other than the over and above physical properties? Well, there are. I mean, the dinosaurs themselves are symmetrical, and symmetry is, I think, a very central mathematical property. And it's out there in the real world. It's very easily perceptible. The same true as ratios. So there's the ratios of heights of different dinosaurs. There's flows, networks. Those are the kind of things I believe are the subject matter of mathematics, as opposed to abstract objects like sets. So I defend an Aristotelian realist philosophy of mathematics, which says exactly that mathematics studies certain features of the real world, physical and any other world, and that there are truths about that, necessary truths. And it's the business of mathematics to study those. So that view very much contrasts with a nominalist view that says it's just a language or methods. And on the other hand, a Platonist view that says that it's about abstract objects in some non-physical world.
What is the difference from your view between talking about something like a ratio as a structure versus using words to describe, a physical phenomenon or a physical structure? What is it that those words are failing to do that math is succeeding to do as a different thing?
Well, you do need the words, obviously, to do it, the same as to study it, the same as you need them to study black holes or anything else. But the things being studied pre-exist that.
Of course.
So, yeah, so if, for example, the four of us all stand next to each other, which we can't physically at the moment, but it'd be easily perceivable what the ratios of our sizes were approximately. So those are things there that a pre-exist language and that language has to capture.
Right. No, I agree with that. I don't think that even those who view math as language would disagree with that, would they? I mean,
well, I think they do, in effect, because they ignore the fact that of the pre-existence of the mathematical structures in the real world. If they are serious about saying mathematics is just a language or just logic, just methods, then they distract attention from that.
Well, I guess yeah, okay, I see what you're saying. Those that would hold to abstract objects would view it that way, but I guess the way I was thinking about it was, any person that's taking a physicalist approach is also going to have a physicalist view of what language is as well, or how language is being used, and yeah.
Oh, that is true as well, which is, of course, very difficult to have a physicalist view of the purely mental and linguistic world. But even so, they're saying that mathematics lives wholly in the linguistic world, so to speak, like, say, grammar. So grammar is not about anything; it's just the way language works. So that is a non-realist view of mathematics. If you thought it was like grammar,
right. Okay, I see what you're saying now.
Okay, if you allow me,
please, yes.
I have a kind of different view on the subject. I understand that many times it is said that mathematical is language. Maybe it's an abuse to talk about mathematics, but I guess that the maybe a best definition for mathematics is that it is a formal system, and this formal system is composed of different terms. There are primitive terms in these systems. There are certain rules that operate with these primitive terms, and there are certain objects which are denoted and represented by these elements in the system. So it's a very complex system, which it's formal, and also it's precise. It doesn't have the vagueness, it's the vaguity that has the common language, the natural languages. So that is why it's a very useful tool, indispensable to do physics, for instance, to describe certain properties of nature. However, I think that mathematical objects are conceptual artifacts. What I mean with artifacts is that these are somehow like tools that have been created by humans, such as a pencil, a book, because they have been created in our minds. These are concepts created in our minds, which are extremely complex. But as you were saying, before human beings on Earth, since there were no human beings thinking or constructing these systems, there was no mathematics at all. The difference between something, in my view, that is material and something that is conceptual is that a material object, a physical object, has the property, a basic property, which is it can change. It has energy. For instance, us, a pen, a book, etc. But the triangle, the number 3, etc., these are abstract objects which cannot change. As you were saying, for instance, when you were talking about symmetry, like if there are some properties, inherent mathematical properties that are in the world, I think that our descriptions of the world are mathematical, but not properties itself of the world. In fact, symmetry is a property that you can find in physics and that many physical systems have, but I won't say that it's a mathematical property. Maybe in mathematics, we can find a better language to describe that physical property. This is my view, which is maybe a bit different from what you have been discussing.
Yeah, I would say that it's definitely, for me, any idea of an abstract object or of some non-physical reality is very counterintuitive to me. I mean, I've never been able to really grasp it. It's always, again, back to sort of what Dr. Franklin was saying, I recognize that it's a hard project to engage in trying to reduce everything to the physical. But I really struggle with conceiving of what it means for something to be real outside of that sort of context. And yeah, maybe, I don't know if David and Dr. Franklin, you want to respond to this other view that was just proposed?
Yeah, I'm sorry. I see a bit of a contrast between two views where Dr. Franklin would say that these mathematical entities are out there. They sort of live out there in the physical world. Daniela seems to be sort of recoiling a little bit from that position, that they're sort of useful tools. In some sense, at some level, it seems to me that one can make the case that some of these structures seem to really be out there. They live out there. You know, you see multiple quantities. You see, that's sort of arithmetic. These are these numbers. You have multiple objects, 3 objects over here, 5 objects over there. Some simple mathematical structures seem to be out there in the physical world. Others, less so. For example, it's an infinitesimal, right? We integrate infinitesimals in math, and we think of these things it's hard to think of them as physical objects, right? But what is an infinitesimal, a thing that's out there? It's even hard to describe. It's very abstract in its description. It's difficult to imagine someone saying that's actually a physical object. You can't actually sort of hold on to an infinitesimal. Is that out there? That seems to be less so. When it comes to physics, instead of simple mathematical quantities like ratios or arithmetic quantity, what about things like F equals ma? There's a relationship, the mathematical relationship between quantities there. Is that kind of a thing out there? At some level, it seems to me that I can kind of visualize it as being out there, right? The math I think of as resisting being accelerated. I have to increase the force in order to get a certain acceleration if I have a certain mass. And these things kind of seem to be out there. And that description seems to live out there in some sense. Then there are other quantities like imaginary numbers. I have no sense of how they could possibly be out there. It seems like we're playing a trick on nature, and so I'm somewhat conflicted there. So I'm not sure what you would say.
Real quick, just David, just be careful because I think I hear your mic feedback a little bit. So just make sure that your microphone isn't hitting something. But yeah, Dr. Franklin, what are your views?
Yes, I agree with David that ratio and symmetry and mathematical properties like that are not in the least conceptual. They're out there, and proportionality, like in F equals ma, F equals ma is a precise language for talking about it, but the proportionality between force, mass, and acceleration is something out there and to be discovered. And how exactly it is out there is a matter for physicists to tell us. And I wouldn't agree with Daniela that mathematical properties are unchangeable in any different sense to physical properties. A triangle, well, real triangles can change their shape, the way that they can change their colors, but the color purple is not itself changeable, just because it's a universal property, and it's physical, whereas shape is perhaps not physical. It's hard to say whether you should call shape physical or not, because probably non-physical things can't have shape. But I would call, say, symmetry a mathematical rather than physical property, because non-physical things could have it. For example, an argument could be symmetrical if the second half repeats the first half in the opposite order or something like that. But an argument is not, a physical thing. If you write it down, you could write it down in ink, but then that's not symmetrical. The argument itself, whatever that is symmetrical. And a palindrome is symmetrical. So symmetry is a mathematical property, the kind that's out there, but not only in the physical world, but in any other world there might be.
Excuse me, I think that here maybe the problem that we are having is precisely that in order to describe these kind of things, we are using our natural language. So when we are talking about symmetry could signify different things depending on the context. So maybe what you define as symmetry in an argument, which it could apply, is different from the symmetry that I'm talking about of a space-time, of the symmetries that some space-time could have. So right. I guess that there is a problem with the representation and with the actual thing in itself. For instance, when you are saying E equal mc squared, if you are writing that on a blackboard, this equation is physical in the sense that you can touch it because you have some, you can touch the equation in the sense that you have particles of, I don't get the word in English, but the E, it's a letter. But in our mind, that letter represents energy, which is a property of a physical system. The M is a letter, but that letter is representing a property of a material system. So, and the mathematics allowed us to express that property that we encounter in nature. And besides, our representations of the world, of the physical world, are not true reality. We are always doing approximation of the actual processes in the world. And we are using mathematics for that. But it doesn't mean that is an actual view of what really happens, which we will never have that view, in fact. So in that sense, I see as mathematics, in some cases, a good tool to represent some of the physical process that happen in the world. Some mathematical objects are very complex systems which have had no application in physics. Some others had, for instance, differential geometry. When Einstein was creating somehow the general relativity, he didn't have the tool to represent what the properties of space-time. And then he discovered with his friend Marcel Grossman that Marcel Grossman knew about differential geometry and show Einstein that this tool could allow him to describe certain properties of space and time, which is curvature, assuming that space and time is continuous, which we really don't know if at a microscopic level it will be. So I guess that maybe the problem is, how do we represent the physical processes in the world? And I think that mathematics in itself is a fiction, but it's a very complex fiction. As we can say Hamlet. Hamlet doesn't exist in the world, it's a fiction. But in the case of mathematics, it's also a fiction, much more complex, with rules, with a system that is consistent, etc., that you can derive theorems, etc., many concepts within the system, but it's still a fiction.
I would like David and James to respond, and then I would like to ask a question for the panel. But David, and then.
Well, so Daniela, what I would ask you is, how do you understand? As I alluded to earlier, right? Electromagnetism is a good example of. So you build these equations, and they have mathematical expressions, and they are relationship between magnetic fields, and you add a magnetic field along some path, and you get this strange relationship with the current, right? You have these equations, and you say that and you describe this as kind of a fiction, a useful fiction, and then out of this useful fiction, I do some other. I play by the rules of mathematics, which produces even more useful fiction from your perspective. Yet it seems to me that I'm getting something real about the world, and it's like the math is tracking reality in a deeper sense, and that I would struggle to use the term fiction there. I guess it's not, it's not maybe 1-to-1. Ultimately, we understand that electromagnetism is a quantum, right? There's a quantum electrodynamics version of that, and I'm thinking of it classically in a certain way, and that's really not the correct, deepest way to think about it. But I'm struggling with the way you describe these mathematical structures as a useful fiction, right? In that context.
I use mathematics as artifacts, which are useful fictions, in the sense that per se, when you don't given a semantical, for instance, when you have, for example, the continuity equation, in the continuity equation, you can, or maybe the Poisson equation. The Poisson equation, in the left-hand side, you have a scalar function, and which is in the context of gravitation, that will be the gravitational potential. But in the context of electromagnetism, that will be the electromagnetic potential. Whereas the density, the rho that you have on the other side of the equation, will represent whether the density of the gravitational mass or the gravitational or the energy density of the electric field. So when you write an equation, you have simply an operator, the Laplace operator, and some scalar functions. Then you say, okay, in the context of a physical theory, you give to those scalar functions a meaning. This represents the electric field. This represents the electric potential, you see? So in that sense, I'm trying to say that per se, mathematics or the objects of mathematics doesn't have a meaning in itself. But when we apply them to the physical world, then we can give them a context. In fact, yes, I'm sorry.
Oh no, sorry. I was going to say. I thought you were done. No, sorry. Finish your statement.
That, as David was saying, that for instance, in the case of general relativity, okay, so tensors and differential geometry is very useful to describe the space-time curvature up to a certain level. But when you go to a level where you have a very small region and the gravity is very high, differential geometry fails in there. So it's not that there is a failure in the mathematical world. It's a failure in our description of the physical world. And maybe we will need another tool, another mathematical tool, maybe that has already been invented, maybe that will have to be invented in order to describe physically what is happening at what we call the singularity.
Dr. Franklin, what is your response to this sort of perspective?
In E equals mc squared, the equation, the symbols E and M are of course ours, but what they express is not ours. The proportionality between energy and mass is strictly out there, and it's discovered by us, not invented. It may be out there approximately or exactly, perhaps exactly in this case, but an approximate proportionality is just as much a realist, a real proportionality as an exact one. And it's the same for Einstein's and differential geometry in space-time. The differential structure of space-time is out there, and it's because it is there and literally true of the space-time manifold, and again, either approximately or exactly, it doesn't matter. Both of those are mathematically real structures. It's because space-time has that mathematical structure that Einstein could describe it with the language of differential geometry, not the other way around.
For my own clarity's sake, am I the only strict physicalist on the panel? It sounds like you all hold to some sort of space for the mind potentially, or the conceptual being somewhat different than some physical account. Am I getting that correct?
Yes, I tend to be a somewhat Cartesian dualist in mind, and I believe in a God, for example, but I don't think that really makes much difference to the questions we're discussing at the moment about, so mathematics, I would say, is literally true of the world, the real world, and whether the real world is wholly physical or not doesn't make much difference to that.
I see.
I just wanted to comment that from what Daniela said, I get the impression that we're sort of on the same page, actually, and we're sort of describing things in a slightly different way. I agree that the mathematical symbols, the mathematical symbols on a page are just symbols. In that sense, the word fiction maybe is appropriate, but when you get them to correspond to something physical, for example, in the Laplace equation, it's the mathematical object is saying, change this thing twice, and that will be proportional to this density of matter. And so in that sense, it's tracking some physical reality in a more direct way, but the symbols themselves are just sort of on a sheet of paper, they're just sort of fiction. So I think we actually on the same page from what Daniela described.
I would say I'm in general skeptical of the idea that when we're applying either math or language, that we are tracking one-to-one that these things are real with certainty in the world, I would say that there's always a gap between the description and the thing itself. But I also wouldn't say that these things are fictions. I think that these are sort of the best tools that we have to try to get to what at least hopefully is the case about reality, even if it's maybe our tools are maybe limited or flawed in some sense. I think I am probably the only strict physicalist on the panel, where I want to say that even what we think of as the conceptual is ultimately reducible to some physical phenomenon. That there isn't this different, two different ontologies operating there. I'm curious to hear what you all have to say about, if math, exists out there. What are things like negative numbers or infinities, or pi, for example? Like, what is it about those, that kind of math that is corresponding to physical reality? Maybe you guys can, go ahead.
Well, pi is, as it always has been defined as, the ratio of the circumference to the diameter of any circle, which is the same for any circle. So what are circles? Well, there may or may not be exact circles in the real world, or probably there are if you take a physicalist view of space, that there are many exact portions of space that are circular. And in that case, well, yeah, the ratio pi is actually out there instantiated multiple times. When it comes to real wheels and coins, well, they're not exactly circles, but the whole situation is structurally stable, as they say, meaning small changes don't make much difference to ratios. So it's a fact about real coins that the ratio of circumference to diameter is quite close to pi. And there's an actual number, then there's an actual ratio close to pi that's instantiated in real coins and wheels. Well, that's mathematical structure, literally, and not in any idealized way in the real world.
What about negative numbers? Like, what sense does that correspond to physicality?
Well, the system of positive and negative numbers is literally realized in displacements on a line, which can be either forward or backward.
Okay, so I'm trying to understand how that then translates into, the physical world that we are part of.
Displacements are a physical world. They're movements.
Okay.
So the physical structure of movements on a straight line instantiates the set of positive and negative numbers.
I see.
So in one direction it would be positive, in the other direction it would be negative.
Yeah, in this case, it's arbitrary, yes.
But for instance, in that case, what I will say is that we know that we assume that we live in at least a space that has three dimensions. We can represent space in 3 dimensions. So in order to represent our movement in space, we can use different systems of coordinates. The coordinates in themselves are abstractions in our mind. And we are using these abstractions to denote, to represent our trajectory in space. So that's what I'm saying when I'm talking about an abstraction. Is something that is our mind creating, but doesn't exist per se in the world. We are using this abstraction to represent some phenomena in the world. For instance, when you were saying about space and time and the manifold, what we know that is real is space-time. We represent space-time. We are assuming that space-time can be represented by a manifold, which is a mathematical object, which is differentiable and that allow us to make certain operations. But one thing is the reality of space-time, which has energy because of we have, for instance, detected gravitational waves, so somehow we can assume that space-time is real. But how do we represent space-time? We are using this differential geometry to somehow describe its properties.
Yes, surely we represent space as three-dimensional because it is three-dimensional. That's the structure it actually has. And the same as with space-time, whatever structure that has, whatever geometrical structure, we hope to represent that with mathematics. But its structure is not itself conceptual, it's what it has.
No, of course. The structure itself is not a fiction, it's real. What I'm talking that is fictional is mathematical in itself. When you say, for instance, the number 3, you cannot touch the number 3 in the real world. You make a correspondence of the number 3, for instance, to different objects. So this correspondence that we are making between our conceptual representations and the real world, this is the link that we are doing in our minds.
David, we haven't heard you for a little bit. Is there anything that you want to add?
Yeah, this this tension between some mathematical structures that seem to be intuitive, that seem to be amenable to a description that's physical. They seem to connect to something that suggests to us that they are sort of out there in the way that James is describing. And then there are other mathematical structures where where all of that clearly falls apart. I mean, you talked about negative numbers, but what about the square root of a negative number? That's an extremely important mathematical object that describes physical systems. The Dirac equation, it's a completely strange mathematical object that is designed to sort of get at the square root of a negative number, and it describes some of the most fundamental objects in the universe, electrons. And yet, I would never say that I have any intuition about any sense that I can sort of see it out there operating. And maybe this is, one might say, well, this is just a feature of human beings. You can imagine aliens that have less intuition about less physical intuition about a mathematical equation like F equals ma that corresponds to something physically. That's physical. That seems to us to be amenable to some physical intuition, direct physical intuition, that we can kind of see F equals ma out there. Maybe the aliens see the Dirac equation in an intuitive physical sense. It would say that's clearly out there in the world. Square root of negative numbers are very intuitive, but somehow from our perspective they're not. So
David,
this bothers me. This bothers me a lot, right?
David, so if you're saying that some of these objects or mathematical objects seem counterintuitive, like you struggle to see how they correspond to anything being out there, well, then what is it that is taking place when we're applying those concepts? Like, what is it that we're doing with math in that context at that point?
Well, if we think in the way that James is suggesting, that these things are actually physically out there, what I'm saying is that maybe that's correct, but we have limitations in our perspective, right? We're human beings. We come at the world from a certain perspective. We've evolved certain structures, perceptive structures to understand the world. They're mysterious to us, but we notice that certain things are intuitive to us and others aren't, and we have some understanding of why certain things are intuitive to us and why others aren't. And maybe we can imagine other creatures that have other intuitions, given different experiences, different evolutionary tracks.
Sure. Go ahead, Franklin.
Yeah, well, that's right. It's worth thinking about some of the more hairy things in the mathematical world and whether they could be physically realized. I mean, maybe take infinities. Well, who knows whether they're realized or not? That's for the world to say. But nevertheless, they're things that could be physically realized. Well, sure, it's possible that the world has an infinite number of atoms in it, as far as we know. And in that case, an infinity would be literally realized in it. It's just that we don't know without observation, which is hard to do in that case, whether that's true or not. Maybe I should mention about the square root of -1. The way we approach it and deal with it is originally a kind of fiction, but nevertheless, it's the structure of the Argand plane with including the square root of -1 and real numbers is literally realizable in motions of the plane, so that the multiplication by the square root of -1 corresponds to rotation through 90 degrees. There's a simple mapping of complex numbers, including the multiplications as well as the additions in physical realities.
Okay, I think I hear what you're saying. Daniel, I don't know if you want to add anything to this.
Well, as an example of complex numbers in application is quantum mechanics. So in quantum mechanics, in the language of quantum mechanics, we are using, for instance, complex numbers in order to describe certain, many operations in quantum mechanics. But I wanted to add another example, and I agree with David in the sense that I sometimes imagine that maybe other civilization, intelligent civilization, could try to maybe understand the physical world, and the language that it develops to understand that physical world could be completely different from ours. And what we have developed mathematics, but maybe they could develop something else, and so that is why mathematics, I think that are a construction of human beings. And what maybe we have learned about the world is that if we assume that there is a world to be known, that there are certain regularities in the world. And somehow these regularities in the world that we call physical laws, we can describe these physical laws using mathematics.
Right.
But maybe these physical laws could be described with some other tool that is unimaginable for us.
I think the aliens have got to get their mathematics right the same as ours. Symmetry, group theory classifies the kinds of symmetries that there are, and that's true in all possible worlds. If the aliens get that wrong, they've got something wrong. Their language, of course, might be different, and their symbols, their mathematical notation is different, but their mathematics needs to be the same.
Right. Okay. So I think
I'm sorry. I think Danilo is saying that maybe they might discover a description of the world that is just as accurate, but is not mathematical. Am I putting words in your mouth?
Yes,
Is
that's
that
right.
Well, they might be discovering some other aspects of the world that we can't see, but if they're going to talk about what we call the mathematical aspects, such as symmetry and ratio, which in the world, presumably they've come and seen our world. If they're trying to study our world that has symmetry and ratio, then they have to get the same truths as us.
I think what's in question is whether or not what we're doing when we're applying these tools is discovering these universal truths.
Yeah. Well, yeah. So if they think the ratio of the circumference to diameter of a circle is 10, then they're wrong.
Right.
Yeah, but they are usually assuming, for instance, the circle, is a mathematical object. A circle in the physical world, we can have approximations to a circle, but it's an abstraction. So of course, inside the mathematical, when you have this formal system in geometry, of course, it's inside this formal system in geometry, the ratio is what you have said, and that's a truth within the formal system. But when you go to the physical world, of course, you will measure ratios, but you will never have a perfect circle. We can measure ratios because there is longitude. We have space dimensions, but these ratios, which are truth inside the formal systems, doesn't mean that will correspond to the physical world.
It does mean that. It means because the real shapes of wheels are nearly circles, and mathematics tells you the ratio of their circumference to diameter is nearly pi. Approximation is not the same thing as idealization or conceptualization.
So James, you think of mathematics as a kind of a set of rules that apply in all possible worlds. That there's no deeper rule book that one could discover.
Yes, I mean, we might discover more that different possible worlds are unimaginably different, but if they have the same kind of properties, quantitative properties and ratio and symmetry, then the truths about them must be the same.
But how would we know, how would we go about justifying that perspective?
Well, that's what proof is for, to justify in terms of necessities. So it's because mathematics is about necessities. We find that it's unlike physics, which apparently you have to just get out and measure and theorize. We have proof that shows that what pi is. Yeah, we can know. Yeah, it's provable that the digits of pi are what they are, and they can't be anything else.
But I think what Daniela is pointing to is that, yes, these are truths within the system that's been constructed, I think is what she's
Yes,
pointing.
that's right. Yes.
And the question is, well, does this truth within the system then carry out into the world in the same way, in a way that is a one-to-one correlation, or even if it's an approximation, one that still is of a correspondence that isn't ambiguous? And well, I think that's what's unclear to me.
Well, if you've got the grant, you can make more and more exact circles, and you can measure their ratios of circumference to diameter more and more accurately, and you'll find they're closer and closer to pi.
Right. I don't know exactly how to ask this because I'm not, again, too familiar with these things, but what do you all make of those people that have used concepts like Gödel's incompleteness theorem as some sort of criticism of the idea that mathematics does correspond in the way that, Franklin, you've just expressed? I've never understood that, how they use that idea as a criticism. I don't know if you guys have heard of anybody doing that. Maybe you can expand on that if you have.
No, I haven't seen people do that. It seems like a confusion.
Okay.
Gödel's incompleteness theorem says something about the possibility of axiomatizing arithmetic, which is a very interesting result. But I don't think there's consequences of the kind you mentioned that could be drawn from it.
David?
Yeah, I've expressed that same sentiment. I think people are confused as to the implications of this.
Okay. And Daniela, I don't know if you want to add anything there as well.
Yeah, I haven't heard about it, but I guess that what Gödel's incompleteness theories point out is that a mathematical system cannot prove its own consistency. I guess that it applies to arithmetics, but it also applies to other mathematical systems.
Gotcha. I guess I'll ask this for a panel as well. I mean, I know that, like I said earlier, I think I'm the only strict physicalist here, but what do you think is the best argument that, from your perspective, that you've heard for physicalism in the context of grounding language, grounding concepts and the mind as still a physical phenomenon? Or do you all completely reject? Is there any argument that's been convincing or at least giving you pause from your worldview from the physicalist side? Or do you think the physicalism in that sense is a failed project? David, you can go first.
Well, my perspective is that there's clearly a difference between the mental and the physical, and normally we think of one quantity emerging. We describe the mental as emerging from the physical, but in all cases where I understand the concept of emergence, it is a physical thing that emerges from other physical things. The best example is, temperature and the motions of molecules. It's one thing, and you're always in that same space. You don't have things of a completely different character. So it seems to me that there's a little bit of a category mistake when we say one thing, what it's like to be emerges from the physical. And so, I don't know how to make money off of that idea, but it seems to me that we have to have unity. That's a message that comes to us from physics, right? We look at different aspects of physics, and the closer we look, the more we realize that they really are different aspects of a more global, unified physical project. And if the mental is to be unified as one thing, it's sort of untenable to have physical and mental as very different things. And then they need to be unified, and so we need to have one kind of thing. And I don't see how to get conscious experience as an emergent physical property. I don't see how I could possibly do that, using mathematics on a sheet of paper in the way that I get temperature from the motions of molecules, which I can do on half a page. So,
Dr. Franklin?
Well, physicalism is a reasonable project in that it offers to explain in principle everything. So the reasons against it must be suggestions on that there are things left over that it's not looking like it's going to explain. And the two main prospects, I think, are consciousness and ethics. So, and I think David is right that we understand quite well in physics what emergence is like, and we don't see how it can apply to consciousness. And I think we're better informed for the last 60 years of artificial intelligence, where it was promised that kind of thing would happen, but it hasn't. It's amazing what artificial intelligence has done with its statistical methods, but actually understanding, there's no prospect of starting where we understand a mathematical proof. The feeling, not the feeling, but the actual understanding is different, completely different to anything that an artificial intelligence can do. And ethics as well, there's a basic difference between explosion of a lifeless galaxy, like it's just a firework, but the death of a human is a tragedy. And there's no prospect of physicalism explaining the difference.
Daniela?
Yes, well, I agree with both of you that emergence is a property of physical systems, and it's quite complex to go from one level to another level. Somehow we can explain emergence as we have some individuals, we have some properties, but the collections of those individuals give rise to a new property that the individuals themselves do not have. For instance, a single electron doesn't have temperature, but then when you have a collection of atoms, the whole system, the fluid, you can assign a temperature. So that's what you will call in an emergent property. So you can start from the most basic systems, from the atomic molecular level, then you will have biological systems, social systems, and so on. And the laws that go from one system to another system are things that maybe we could someday understand, but there must be some way to go from one to the other, these emergencies, because we see them in the world. And one of the most striking of all these examples is, of course, consciousness. These processes that happen in a brain that give rise to consciousness. And at least my little knowledge of neurosciences, there has been quite a progress to understand consciousness in the last decades, but there is not a clear understanding. Maybe what we can say is that there are degrees of consciousness in individuals. We cannot say that there is a, like something is not conscious and then conscious. For instance, when you have a pet, your dog, somehow you can think that it's some sense of consciousness it has. Maybe not the same degree of consciousness that a human being. So maybe you can trace some kind of degree of consciousness in different individuals. Or the way some kind of animal have consciousness is different from ours. So it's a matter of study, I guess, and there are many questions to ask. And I don't know, since our brains are limited, I don't know how much we could understand about that phenomena.
We're about to hit the 1 hour mark. I don't know if I'll give you guys a chance to do some closing statements, and then I'll respond to what was just said with my perspective. And then, again, I appreciate everybody's time, and thank you for coming on. So David, and then Franklin. Anyway.
Yeah, sorry. No, I love these conversations. I think this conversation put my confusion a little more in context. I normally don't think about these kinds of things. What is the deep relationship between mathematics and the physical world is still something that I don't think I really explored, certainly don't understand very deeply.
Well, I just urge people thinking about mathematics to always keep in mind what it is about the real world that a certain piece of mathematics is trying to tell us about, symmetry, proportionality, whatever it might be. You'll find something, and that's not just conceptual. And I suggest pursuing an Aristotelian realist philosophy of mathematics to give a sense of that.
Well, I want to thank you for this talk. It's very nice to have different perspectives on this. And maybe my final thought of this is that what I think is that we have a way of thinking the world mathematically. And maybe what I was just thinking that maybe these properties of symmetry and ratio that we are thinking in a mathematical way, maybe are also physical properties of the world that we are trying to put in a mathematical context.
Sure. I'll end it here. I'll say this in the context of consciousness, and I think also ethics was mentioned briefly. I agree with the idea that we can't reduce consciousness to a mere description, right? Because we are operating through consciousness. It wouldn't make any sense. I don't think that if we're looking at a brain state that we can say there's consciousness, right? But I don't think that that's necessarily a problem for physicalism, at least not sort of my version. Because I don't think that reality or truth is ever reducible to just the mere description. I think there's always a gap there between the description and the thing itself. And I'm not convinced that even in our limited way of talking about consciousness, this leads to the need to assume some other ontology, that somehow, because there are these limitations, both subjectively speaking and in terms of our descriptions, that therefore consciousness is some other thing than some physical process. Which again, when I'm use the word physical, I don't mean just measurement. Maybe that's where I think maybe I tend to differ with a lot of physicalists. As far as the talking about, physicalism can't attest for morality, I think it can, if by morality we mean harm reduction. I think I'm not convinced that, like, I tend to think that is-all problem distinction is illusory. I think when we're talking about oughts, we're actually talking about is statements. When we're talking about moral goals, we're talking about harm reduction. And I think those things can be measurable in very real, tangible ways. And but I recognize that sort of my view on these things tend to be in the minority. But maybe we could have a secondary conversation, if you guys are willing, about consciousness and morality in more detail.
Yes.
But
Yes.
I appreciate you guys coming on and sharing your perspective and your time. And to the audience listening, thank you as always. Hopefully we'll come back with another episode soon. And I wish everybody a safe night. And thanks again. I'll talk to you guys soon.
Thank you, everyone.
Thank you.
Thank you.
Very
Thank you very
enjoyable.
much.
Thank you.
Thanks.
Number 3, all